Hi Holly, thanks for the questions. Hopefully this sorts them out for you. So just pick them out and we'll go through them. There we go. So first one's just worded questions. It's algebra. So Ben and Chris are twins. So whatever age, whatever expression we use for one of their ages, we'll use for both of them. So whether Chris is, Ben is too, and their brother Stephen is 4 years younger. So, and then finally the total, so adding up their ages we get 17. So write this information in an equation in S, Stephen's age. So Stephen's age plus Chris's age. So Chris's age must be S plus 4 because he's 4 years older. Okay, but so is Ben, so then we could have two lots of S plus 4, and all of these ages must add up to 17. Okay, so if we expand this, then we get S plus two lots of S, which is 3S, plus 8 equals 17. All right. Then the next one's relatively similar. So Chris is 3 times as old as his son Joe now. Okay, and in 12 years' time he'll be twice as old as him. So given that Joe is J years old now, write an expression for Chris's age in 12 years' time. So Chris is currently 3 times as old as his son. So then to find Chris's current age, we would just literally take J and times it by 3. But in 12 years' time, it will just be 3 times J plus 12. Okay, or just write it easier, there we go. So that's Chris's age in 12 years' time. This is his current age, 3 times as old as his son, but then 12 years more. But we're also told, so that's part 1. For part 2, to find an equation, we can also, there's another way to find Chris's age in 12 years' time, because in 12 years' time, he'll be twice as old as his son. Okay, and the important thing to remember is Joe will also be 12 years older at that time. Okay, so Joe's age will be J plus 12. And then his dad's age will be double that. Okay, so then there's the equation that we need. So this is how old he'll be in 12 years' time using the first part of the sentence. And this is how old he'll be in 12 years' time using the second part of the sentence. And then of course, because they're both in 12 years' time, they're both equal to each other. So in solving this, if we expand this, we get 2J plus 24 and 3J plus 12. Take away 2J from both sides, gives you 1J on this side, and take away 12 from both sides, gives you 12 on that side. And there we go, got our answer. Okay. For this one, there isn't really a, I would imagine if you've tried it and got it wrong, the only place you've got wrong is this negative sign here. Okay, so if we expand this, just like regular double brackets, so x squared times x is x cubed, and times 1 is x squared, and then minus x, and then minus 1. And here's where perhaps just make your life a little bit easier. Put a minus sign in, and then put some square brackets to denote the expansion of these two, because we're taking away all of whatever we get here. So I'm going to write that here, and then take it away. So we get x cubed again, and then we get minus x squared, and then we get 1x, and we get negative 1. So now I have to take away each one of these terms. Okay, so x cubed minus x cubed is nothing, so they cancel. X squared minus minus x squared is like add x squared, so now we're up to 2x squared. Negative x, take away that x there, that's minus 2x. And then negative 1 minus minus 1, so negative 1 add 1 is obviously 0, so then there we go, we just end up with that expression there. Right, and finally for this one, if you have done 5 part 1, 2 and 3, because you've only asked for 4, then this can be super useful for the next bit of further maths from the binomial expansion, which makes these really easy. The only reason this question is here is to help you understand a pattern that forms when you do these expansions, okay? So all I'm going to do is reorder probably what you've already done and then show you to help you find the patterns. So I said this will be useful for next week's further maths work. So if we expand this, that just means a plus b times a plus b. So if I expand that, I get a squared plus a times b plus another a times b, or ba, which is the same, b times a is the same as a times b, so I'll just write ab again, plus b squared. Okay, and if I simplify that, and that's the important bit here, I get a squared plus 2ab plus b squared. Now, for a reason that you won't spot right now, I'm just going to write 1 there and 1 there. It's obvious it's 1, but just for a pattern that we're going to spot. Now, a plus b cubed, let's do that down here. So we'll do a plus b times a plus b first, and then we'll multiply it by a plus b. So let's get this. So we already know a plus b times a plus b is this. So that equals a squared plus 2ab plus b squared. And now we're going to multiply that by another a plus b. And take our time. So a squared times a, which is a cubed. And I've got a squared times a, which is a squared b. And then we have got 2ab times a, which is 2a squared b. And then we've got 2ab times b, which is 2ab squared. And then finally got b squared times b, which is b cubed. Okay, so looking through these then at the pattern that has formed, I feel like I've missed a term. Oh yeah, I didn't do b squared times a, which gives us ab squared. There we go. Okay, so tidying this up, we've got a cubed, and we've got a squared b here, and then later on we have got 2a squared b here. Okay, so then in total we've got 3 lots of a squared b. So if you use this, this, and this. Now here we've got ab squared and another ab squared, 2 lots there, so 3 in total. And then finally we've got this b cubed. Okay, and again I'm going to put the 1's in. So in this order we've got 1a cubed, 3a squared b, 3ab squared, and 1 lots of b cubed. Okay, now I'm just going to point out a couple of things right now, patterns which are emerging. In writing it in this order, the order that I've got it in, the powers of a are decreasing each time, so 3, 2, 1, and 0 if you like, there's no a here. And the power of b is increasing, so no b here, but then b to the 1, b squared, b cubed. And then we've got the numbers 1, 3, 3, 1. Okay, so in the first row we had 1, 2, 1, and the next one we had 1, 3, 3, 1. And this forms what's called Pascal's triangle, where if you add together two numbers from the previous row, you get the one in between. So for instance, 1 add 1 makes 2, there, okay. 1 add 2 makes 3, 2 add 1 makes 3, and then obviously you get 1 add 0 each time, so the outside term is always a 1. So the next row would be 1 on the outside, 4, 6, 4, 1, because 1 add 3 makes 4, 3 add 3 makes 6, 3 add 1 makes 4. So there's more of this in the further maths coming up, the binomial expansion step, just to explain how you can get these numbers. And then finally, for this power of 5, 1, you'd have 1, 5, 10, 10 again, 5 and 1. That's from adding those two terms there to get that one. And then so we throw this all together. So it's a bit of a leap of faith, but to find the pattern, got 1 minute 10 seconds left in this video. So I'm going to leave the a, well, let's write the a plus b to the power of 4 one. So the a plus b to the power of 4, you should have got a to the power of 4, okay? Now what you'll notice is these numbers here, I'm going to pop in front of these a and b terms, okay? So a to the power of 4, so 1 lot of that, so I've used that one, plus this is going to go down to a cubed, and then we're going to introduce the b to the power of 1, but then we're going to take this coefficient 4, so hopefully this is what you got when you expanded it, plus the next number is a 6, lots of a squared, b squared this time, so that went down by 1, the a's, and then up by 1 for the b's, plus 4a to the power of 1, b to the power of 3, plus b to the power of 4, and 1 lot of that, and no a's. Okay, so this is going to drift into another video, sorry. I'll just stop and go again.